Okay. By the way, that camera can only record the upper half of my body. So whatever I did down there is not going to be in the video. So you should show up to the lecture in order to see that. Okay. All right. So as a first course of physics class, let's first ask what exactly is physics. There are a lot of schools in academia, not all of them in science, and among all those scientific majors, not all of them is physics. So what exactly is physics? So in physics, we try to describe the world in a fundamental way. Fundamental, yeah. So what exactly do we mean by fundamental? When something is fundamental, it should be beyond like human being. It should be beyond race, gender, social class. It should work the same for anyone. So one specific case or one specific characteristic that a physics law should have is that a physics law should work the same for anyone. It should work the same for anyone because it's fundamental. It's not fundamental if it doesn't work for anyone. So pop quiz, let me write down something and you decide whether it's a physics law or not. Let me say, I claim that cilantro smells good. Do you guys know what is cilantro? Cilantro? Alright, so I came up with a law called cilantro smells good. Is this a physics law? Why not? It doesn't work for everyone, right? Is there anyone here that don't like cilantro? Good, so this law doesn't work for anyone. Therefore, it's not fundamental. We know if it doesn't work for everyone, then it's not something fundamental beyond like the DNA of your structure. We're not talking about DNA for a specific person. We're talking about some law more fundamental than that. So this is not a physics law. Now, if you get your degree in UC Davis, and then you go back to San Francisco or Los Angeles or our city, and they told you that, oh, physics law works different here. You have to take physics again, then you will be very mad. So if physics is fundamental, it better work the same everywhere. Okay? So another pop quiz. Now I claim I have another law which says July is hotter than January. That sounds right. This is almost July now, it's super hot out there. Alright, is that a physics law? No, it doesn't work everywhere, at least not in the southern hemisphere. People in Australia is having winter right now. Do you guys know that?
Yeah.
Okay, good. So this is not fundamental because it doesn't work for anywhere, or it doesn't work at anywhere. It's not for Australia. So this is again another physics law. Finally, if you learn your physics law today, and when it's time for your final physics law change, then you're screwed. So it better work the same today and tomorrow and forever. So it should work the same at any time. So that's the basic requirement for a physics law because we want it to be fundamental. So final pop quiz. Woman can't vote. Is that a physics law? No, because it is not true anymore. If a physics law is fundamental, it should be true forever. This is no longer true, so it's not a physics law. Okay? So physics is something that should be fundamental. And I tried to come up with some physics law, and as you can see, I failed 3 times. So it seems like physics is hard to come up, and that's true, but it's not that rare. There are a lot of physics laws out there, and the physics law that we're going to learn in this class is the one originated from Isaac Newton, called Newtonian mechanics. That name makes sense. Is originated from Newton, yeah. And we usually teach it as the first class of physics because it's easy. Okay. Some other famous example is like quantum mechanics. That is also a physics law that satisfies all our requirements, but we're doing Newtonian mechanics in this class. So in Newtonian mechanics, there's some other thing that tells you how we try to construct a fundamental law. In Newton's imagination, everything is made up with point-like particles, including my pufferfish. So if you take a microscope, a very powerful one, and you try to keep zooming in to whatever you're looking at, in Newton's imagination, you should end up seeing a bunch of points, like particles, just moving around. And whatever you see microscopically will just end up being the kinetic motion of this particle. So if you see a pufferfish swimming, then this is how my fish swim. And if you zoom in, you'll just see a bunch of particles probably moving in some weird way, but as a whole, they should all move towards some direction. So the pufferfish should be swimming microscopically. Okay. So this is another way that we try to construct fundamental law, because we are studying the motion of these particles, which is the fundamental building block of everything. So if everything is built with these particles, then they are fundamental, because it builds up everything. They are the fundamental building blocks. And our plan is to study just the motion of these particles. If we know how these particles move, we can know how everything moves. Because like my pufferfish is filled with particles. If I figure out how every particle filled out my pufferfish moves, then I can know which direction it's swimming. A soda can is also made with particles. So if I try to throw this soda can away, I can just look at all the particles that filled up this soda can and see how they move, and then I can predict where this soda can microscopically will fly toward. So theoretically, I can also predict the number of the lottery, because lottery is just 60 balls bouncing around in a cage, which is just 60 bunches of particles that are around in a cage. So if I can calculate how every particle moves in each ball, I can figure out which ball will come off first, and then that's the lottery number. So that's Newton's idea, okay? And in this class, we will start by studying the motion of particles, and then tell you how to build up a microscopic description from these small particles. Now, before we do that, let's do something that is more important, called dimensional analysis. So before we try to do anything, let's understand what type of thing are we doing or are we analyzing right now. There are only three types of things. There's only time, there's length, and there is mass. There's only these three. That's the only three types of things. And all other things are some combination of those. For example, if I said I'm 23 years old, what I'm describing is a time, the time that I've been born and stay on Earth. So the way we denote that is to put a square bracket around that thing, which means that I only care about what type of property or what type of quantity is this thing describing. I don't care about 23 because it's just a number. I care about that this thing is describing some time, which we use t. So for time, we use t. And that's how we denote just analyzing the dimension of that quantity. Have you guys done this before? Yes? No? Should I skip it? Alright, don't skip it. It's very important. It's the most important thing in this class. You are learning it right now, and it was showing all your exam. Yeah. So let's say I want to describe my height, and I say I am 5 feet 8, and that thing is some kind of length. I don't care about 5 and 8; those are just numbers. When I look at the dimension, I only care about what type of quantity that number represents. So for length, we use L, because length starts with L. You can guess what represents mass. It's going to be M. So if I say I am 155 pounds, that quantity is describing some type of mass. And we denote it as the dimension of this 155 pound is mass. Okay? So those are the only three types of dimension, and that's it. All the other quantity will have dimensions in a form of those three combinations. Let's say I want to compute the area of a rectangle. By the way, is this visible for all of you? Good. So if I want to compute the area of rectangle, I know the formula is side times side, right? Okay, good. Now, if I want to ask what is the dimension of area, I just put square bracket, meaning I